Hello everyone, welcome to the second week of the course, Automating GIS Processes Part 2. Sorry that I couldn't be there in person for this lecture, but from next week on I will be back on campus and we will have these lectures on site as usual. Um, Today we are going to get to know GeoPandas library. Finally, I've been talking about it for a while. Um, so things start to get even a bit more serious and interesting, and we will start to do some real GIS from this week on. So last week we had a bit of introduction to the course, so we know what to expect from this course. And we also worked with Shapely library. We learned how to work with geometries, and that will hopefully provide us with a better understanding of how GeoPandas work, because under the hood, GeoPandas uses Shapely to work with geometries. Uh, yeah, so that's what we are going to do today, get to know GeoPandas. As you can guess from the name, GeoPandas is a library that is built upon Pandas library, so it has almost all the functionalities that come with the Pandas package, but also it brings us some additional geospatial functionalities. So there are a lot of things we can do with GeoPandas related to geospatial data handling and processing. So yeah, today we will start by getting to know the GeoPandas library. We will have a bit of introduction to see how it works, and then we will see how we can read and write special data from different formats. We will learn how to filter and regroup data by spatial and non-spatial characteristics. We will work also with coordinate reference system, or CRS, which you hopefully know is a very important part of handling geospatial data. So we will see how we can read the CRS of different data and transform them to other systems if necessary. Uh, yeah, we also will look at a few other things. We will start actually our work today by looking at how to manage file paths in Python. So it's not necessarily related to GIS, but it's a very uh, important skill to have. So we will have a look at that at the beginning, and then we will also talk a bit about vector data before we get started with GeoPandas. So let's get started and see how we can do GIS or automate our GIS processes using Python.
Okay, so before we continue, before we get started with what we have for this week, let's take a quick look at what we had last week. We ran out of time, so we had to go through some of these parts a bit more quickly. So let's take a quick look at this again. So yesterday we went through how we can define geometries using Shapely library. But since we ran out of time, we were a bit like faster in these parts. One thing that we looked at last week was some of the methods and properties that come with polygons and polygon classes in Shapely library. We could, for example, see how we can calculate centroids of a polygon by just using dot centroid, or get the bounds or area uh, or exterior. One thing that I mentioned but we didn't really look at was getting the interiors of a polygon. So uh, that is the case. For example, if you have a polygon with a hole like we have here, then we can get the interior boundary of that using interior method. As I mentioned, what we get as output, but the exterior is 1, like we saw here, but with interior, since there's a possibility that there might be multiple holes in the polygon and therefore you would have multiple interiors, what the library returns to us is basically an iterator. So if you want to access the interiors of a polygon, then you have to iterate through it. And we have seen this already. So we can write, for example, a for loop. So I will go with the polygon that had a hole. So for, let's call it interior. So for interior in, this is the name of our polygon, and in order to access the interiors, we use interiors in plural. Then let's just print out the interior to see what we are getting from this. So as you can see, it gives you the coordinates of the interior boundary of our polygon. So it's an iterator. Here in this case we only had one hole, so it just gave us one, but in case there were multiple, then this for loop would have printed multiple for us. Another thing that we did not look at last week, since we did not have enough time, was this check your understanding part, where we were supposed to practice how we can define some of these shapes using what we learned about geometries, working with geometries in Shapely library. So defining a polygon, defining a pentagon, we have the coordinates already. So in order to define that, you just define it as a polygon. So I just copied and pasted the coordinates from here. So it's a simple polygon object. So if you just run this, you will get the output, which is a pentagon. For a triangle, so we can use whatever coordinates you want, but I can go with one simple example, and I'm going to define my polygon using these, my triangle polygon using these coordinates. So the first node of my polygon will be at 0, 0, which is simple, and I can have the second node would be at 2.4, and the third node would be at 4 and 0. So I forgot to put the brackets. Yeah. And of course, this polygon, the whole thing should be in a bracket. So let's open and close that. Yeah, so this way we can create a polygon. For square, again, you have to be a bit creative with how you choose the polygon so that the result turns out to be a square. I will go with, again, some simple coordinates. So the starting point of my coordinate, my square would be at 0, 0. Then I will have the other node at 2.4, 2 and 4, or let's go with 0, 4. This is square, so we need 4 nodes. The other one would be 4 and 4. Then let's put the fourth one, and that would be for me 4 and 0. So the x and y coordinate. Let's just run this, and this way we get a rectangle. We already quickly looked at the buffer, so this is how we can apply a simple buffer with Shapely. Of course, you first define your point, and then you apply a buffer with a unit. As I said last week, here with Shapely, we don't have units. We don't specifically define units, so the unit can be basically anything. So in this case, we just apply, create a point at coordinate 0, 0, and then we apply it with the unit of, apply a buffer, which will create us a circle around the point with a radius of 1, whatever the unit is. Okay, so now let's take a look at a course's website and get started with the second lesson. So in this second lesson, as I already mentioned, we are going to work with vector data. So we are going to start using the library GeoPandas, and shortly we'll take a look at what GeoPandas is about and how it works, but we will learn a number of things essential for working with vector data in GIS this week. So that's the overview of our lesson for the week. But some of the key concepts that are nice to maybe review before we get started, in order to make sure that we all are on the same page and what we are knowing, and we know what we are talking about. So some of the key concepts that we will use a lot during this course, starting from today, are reviewed here. So let's make sure that we all know what is a shapefile. So a shapefile is a vector data format for storing location information and related attributes. a shapefile consists of several files. So the name itself might be confusing. When you save your data, your vector data as a shapefile, what you get as the output is not actually a single file, but it consists of a number of files that have different extensions. So you have your geometries, your main shapefile file as a .shp file, but you also have other things such as .dbf where you store your attribute data. There can be a .prj in your shapefiles list of files where you store information about the coordinate system and the projection used. So shapefile is a data format that is a bit old. It was developed by Esri many years ago, so but still it's used, especially if you're using ArcGIS and Esri products. But many people nowadays favor GeoPackage as a data format for storing vector data. It's an open source format for storing and transferring geospatial information. GeoPackages are able to store both vector and raster data. So basically what a GeoPackage is a container for an SQLite database with a .gpkg extension. The GeoPackage format is governed by the Open Geospatial Consortium, or OGC. So it's nice because it is a bit more modern than shapefile. It has more features, more qualities. For example, it works for both raster and vector data. And of course, it's a nice thing that it's an open source thing and not tied to a commercial product. So we will use GeoPackage data quite a lot during this course. Another thing that you will hear about quite a lot during this course is CRS for short, or Coordinate Reference System. And a coordinate reference system defines how coordinates relate to real locations. So we already saw in the first week when working with geometries, well, we have a coordinate system, but coordinate system, when it's not defined, we don't know where it is exactly, or what is the unit of analysis. Is it in meters? Is it in kilometers? We don't have that kind of information. But when a coordinate system is clearly defined, then you can relate those coordinates with the real world. So you can pinpoint it to a real location on Earth. Geographic coordinate reference systems commonly use latitude and longitude degrees, while projected coordinate reference systems use x and y coordinates to represent locations on a flat surface. So depending on what we need, you might go with a coordinate system or a projected coordinate reference system. Yeah, but today already but the assumption in this course is that you know basics of GIS, so I assume you know what we mean by projected coordinate systems and coordinate systems, so we are not going to cover that. But today we will learn how to work with coordinate systems using the libraries that we use in this course. Another concept that is important in our work is datum. So a datum defines the center point, orientation, and scale of the reference surface related to the coordinate reference system. And that is something that comes with our definition of coordinate system when we are working with those. Another term that you will see quite a lot during this course is EPSG. It's a short code for referring to different coordinate systems. And it stands for European Petroleum Survey Group. So yeah, so it started with a whole different intention, but then it was more globally adopted for simply referring to coordinate systems because it's simple. You can just use a code without any confusion to refer to a certain coordinate reference system. For example, in Finland, we use the ETRS TM35 Fin quite a lot, and the EPSG for it is 3067. So it's a bit shorter, easier way of referring to a coordinate system. Another coordinate system that we will see a lot, especially when we are working with web maps later on during this course, is 4326, which refers to the WGS-84 coordinate system. There's a link here if you want to learn more about different coordinate systems and their EPSG code. You can just follow this link and learn more about those. Okay, so now let's start working with our materials for this week. And before we get started with doing some actual GIS, let's learn something quick about managing file paths. It's a very important thing. It's not limited to GIS, of course. It's about more like general programming skill, Python programming skill, and it's a good habit to have. So managing file paths systematically is a good habit to have, especially if you want to run your code on multiple computers, if you want to share your code with others. So one thing that we have already seen, I guess, in the first course is that try to avoid absolute paths to file, because unless you're always running the code on the same computer and not moving anything, this is recipe for error essentially. So if you choose to share your file with someone else or run it on another computer, or if you move around the files, then you will get an error. Another problem that we often have with path is that different operating systems use different signs. So for Linux-based machines, including Mac computers, directories are separated with forward slashes, whereas on Windows we use backslashes. So if you are using backslashes, it works fine on a Windows computer, but if you share your code with a colleague of yours who is using a Mac or a Linux-based machine, then they will run into error because backslash is not used for dividing, separating directories. So that's why we will today learn how to be a bit more systematic with these things. Previously, there have been other ways of working this out, but starting from Python 3.4, so very recently, now you're working with Python 3.11 in this course. And there is, I guess, the latest version at this time is 3.12. So yeah, so starting from 3.4, there is a built-in library coming with your Python package called pathlib that provides you with some good solutions how to make your code more interoperable. So pathlib provides an abstract layer on top of the actual operating system file path that is consistent across computers. So if you use this, then you share your code with someone else using a different operating system, you should not run into problems. So I have already, before we continue, let's make sure we have pulled the latest changes. So I'm inside our directory and I have already used Git plugin to pull the latest material for this week. Once you do that, you should have this folder called lesson-2 under your lessons folder. I have already done this, so let's get started. Yeah, so the first thing you need to do is to initiate a file path. So using pathlib.path, you create an object. You can initiate an object with a file path as a string. When created without an argument, it refers to the directory of the script or notebook, so where you're running this code from, and that allows you to handle things relatively, which is a nice thing to do. So let's get started and see how this works. So I will start, of course, by importing the library. As I said, the library comes with your Python installation since Python 3.4. So you don't have to install anything, you just need to import it and start working with it. So I will import a library that is called pathlib, and from pathlib I'm going to use the function path to initiate the process, initiate the path object. So if you run this, this is the output again. So far the path is not checked against the actual directory structure, but if you want to do that, we can just resolve it and convert it into an absolute path. So if that's what you need, then you can get the absolute path in this way. So I'm starting, I will use a variable named path, and first I will create the path object using pathlib.path. Note that the path is with capital, and then I'm going to resolve this to get the absolute path. So path.resolve, and then I'm going to just see what I get as the output. So this is something that we will be doing pretty much every week during this course, because it's a good habit to have, and there might be some of us who are using running this on different operating systems. So if you run this, then you can see the absolute path to your folder where you have your script and you're running it. We are running this script from this directory. So if you are doing this in a different computer, probably for you it might look different, or if you're viewing the course's website, which is running on read the docs, then the directory path probably looks different. But now we are doing this in CSC environment, and this is how the path looks like for us. So the path object has a number of properties and methods that are useful to give you some functionalities working with path. One of these methods is path.exists. So path is the name of the variable where we have stored our path. And if I just check exists, it's going to tell me whether that path exists or not. Is it a correct path? Does that directory or file exist? And it returns a Boolean value for me. So in this case, it's true, the path exists. Another thing you can do is to test, to check whether the path refers to a directory or not, because the path can, of course, also refer to a file. So using is directory, it's short for is directory, you can check whether the path is referring to a folder or directory. And the output is again Boolean. In this case, it's true, so it is a folder that we have in this path variable. There are other things you can do that we will not do right now, but the code is here. So you can use path.rename to give a new name to your file or directory. If you use path.unlink, you can delete if the path is a file, or if it's a folder, if it's a directory, then you can use path.rm there, remove directory, and it will delete the directory for you. But in this case, we are not going to delete anything or rename anything, so we will skip that. But it's good to know that you can do these things using this library. Another useful thing that we will use a lot is, of course, traversing within the path. So, and for that we use, depending on different operating systems, you might be using a forward, a slash, or a backslash. And that's where things get tricky if you are running the code on different operating systems. But the good news is that when using this library, you don't have to worry about that. To refer to a directory inside your path folder, we just simply use the slash as the division operator. It is a division operator, so to append another path component that can be a string. So for instance, if you're inside now we are inside the lesson 2 folder. If within our folder we have another folder called data, if you want to change the path there or go into that path, you can just put this division operator and just put the name of the folder to get to that folder. So this is something that we will be doing a lot. So if you want to define the path to our data directory, which we will use during the lesson, so I just define the path inside and store it in the variable called data directory. And path is the absolute path we have already resolved using this library. So if you want to get the path to the data folder, I just put up this slash sign, and then you put the name of that directory that you want to get into. So in this case, it's data. So regardless of the whatever operating system you're using, this should work for us. So now I'm going to just put the name here to see if I did it correctly. So it was called data underscore directory. So if we run this now, we can see that we have the path to our data folder. So if you have your data stored there, it's just easy. Whenever you use this path, you will get the path to your data directory. To refer to one directory up from a path, you can use .parent. So now in the path, yeah, so let's just quickly look at that. So to refer to, yeah, so if you have path.parent is going one step back. So if you remember with path, it was referring to folder lesson 2. Of course, if you go to the parent one step back, it will be the lessons folder, and that's what we are getting as the output here. So it goes to the parent of that directory. So path objects can be used almost anywhere. A file path is expected as a variable of type string, so it automatically converts it to so if it's a string that is required, it will automatically take care of that, so you don't have to worry about it. In data science projects, it's a good habit to define a constant at the beginning of each notebook that points to the data directory. So if you have it at the beginning, then if it needs to be updated, it's simple. Just do it at the beginning. You don't have to go through all your code. In Python, we don't have a way of defining constant variables like we do in some programming languages like C, but it's a good coding practice. So if you want to define something as a constant variable, although it won't be really constant, it's a standard, it's a good habit. If you define it as in all capitals, then whoever is reading your code knows that, okay, this variable is treated as a constant in your code. So this is something that you will see almost every week, that we import the library, we define the path, we resolve it, and then we give the path to our data folder, name it data directory in capital, suggesting that it's constant. We are not going to update it during our lesson, during our work, and then we use this to access different data. So this is something that we are going to work with today, but just quickly looking, we will be importing GeoPandas library, something that we will learn about quickly. Then we can read the file like this. So we have defined the data directory. Let me run this cell. So now data directory is defined. So if I want to access a folder, a data set, which is in GeoPackage format, inside that data directory, inside another folder called Finland municipalities, this is just how you do it. So you have the data directory defined. Then if I can show you here, inside there we have another folder called Finland municipalities, and inside there we have this GeoPackage save. So we are basically referring to this file here. Yeah, so this is important. So we will be using this a lot. So you will get to practice this, and it will start to make more sense and be more comfortable for you as we progress during this course. But now it's time to continue with our lessons and do some GIS. Okay, so now let's continue. We open the next notebook file. It's called vector data. So let's learn about the basics of vector data and how we can use Python to read the data. So one of the first steps of many analysis workflows is, of course, to read your data. So if you're working with data sets, you need to read the data. Another step, which is usually at the end of your analysis, is of course to write the data. You do some analysis, you might change your data or produce a whole new data set, and at the end, usually at the end or different steps of your analysis, you might need to export that data to an output file. To the horror of many geoinformatics experts and scholars, there are so many file formats in GIS, so you might have, well, nowadays it's less of a problem, but especially in older days, it was just hard. If you're using different software, it might be a bit confusing and a bit annoying that there are so many formats that may not be supported across all software. So there are formats such as Esri shapefile, which are old but still used quite a lot. There are also universal formats such as the geo package that we already talked about, and there are also web optimized formats such as GeoJSON. So these are just a few examples of formats that can be used for storing vector data. But the good thing here is that we should not worry about these formats much when working with Python, because Python can read them all. Of course, there's no guarantee, but most files that you would get, you will find probably you can just read them in Python without problem. Most of the current Python GIS packages, including GeoPandas that we are using in this course or later on when we work with raster data, they rely on GDAL OGR libraries, which are huge libraries for doing many GIS operations. So they build on this library for which modern interfaces exist in the form of Fiona or rasterio Python libraries. Rasterio is something that we will see later on when working with raster files. So today we will concentrate on vector data. We are not looking at raster yet, so let's take a quick close look at Fiona's capability. So Fiona is a library that is built upon GDAL, and it allows you to work with different files for reading and writing. And we will be using GeoPandas during this course, and GeoPandas is using Fiona for handling reading and writing of different vector data data formats. So that's what we are going to do, even if you're not explicitly using Fiona during this course. Other than this lesson, you will see that we are using Fiona under the hood in GeoPandas. So let's start using what we already learned today, and that's defining our file path a bit more systematically. So this is something that you will see pretty much every week. We import the library pathlib, we find the path to our script and resolve it to get the absolute path to it, and then we define a data directory, which is under data in the current directory where we are. So I will just run this so the data directory is defined. So as I said, GeoPandas under the hood uses Fiona. Let's take a quick look at what drivers Fiona supports, which format. So let's run this. You will get an error that the module is not installed. So let's just quickly install the library. So we can just do this from Jupyter Lab. So this is not just for this. If you want to install any library you need for your work and it's not pre-installed in our CSC environment, then you can just use it, for example, using pip method. So one thing is that the data is wiped out every time you open a new instance. So if you now install this library, next time probably it's not there, but now I will just quickly install it since we don't have it pre-installed, just to show how it works. So I'm using pip method to install the Fiona library so that we can see how Fiona works and what formats are supported. So please note, this is, well, at least the last time I checked, when you install a library through your session, then it will be wiped out next time you run it. So yeah, so I used pip to install Fiona. You can also use conda, other methods for installing your library. So now I can import the library and check the supported drivers, and there are these R and W signs. So R marks file format that Fiona can read. So for example, with DXF, it can read and write. W refers to writing. and then there's A if Fiona can append new data to existing files. So with CSV it can write, read, and append. With some of them, like topo.json, it can just read or write for GML, but not append. So these are some of the functionalities with different drivers, different file formats that come with Fiona. And since GeoPandas uses Fiona, this applies to us when we are working with GeoPandas. So let's see how we can read and write geospatial data. So Fiona allows very low-level access to geodata files. This is sometimes necessary, but in typical analysis workflow, it is more convenient to use a higher level library, and in our case it's GeoPandas. So we don't explicitly use Fiona for our work, but if we need lower level access to our geodata file, then Fiona can be used more explicitly. But now we just use GeoPandas to read our data. So finally we are using GeoPanda. Soon we will take a closer look at how it works, but for now let's just import the library so we can use it to read our data. So I import GeoPandas. It is very common to use the short name GPD for importing GeoPandas, just so that you don't have to type the whole thing. But now let's just go with the full name. So I'm going to load my data, the borders of the municipalities of Finland, and I'm going to store it in a library, in a variable called municipalities. So this is how you can read the data, very similar to what we used to do with pandas library. So using GeoPandas, I can use the function read underscore file, and then we provide path to our file. Remember that we already ran the first cell, so the data directory is already defined, but I have to explicitly go to that file that I'm reading here. So it is inside another folder called Finland underscore municipalities. Very difficult word to type. Hopefully I don't have any typos here, but yeah. So inside that folder there is the file that we want to import, and that is called Finland underscore municipalities underscore 2021, and the extension of the file is a GPKG, is a GeoPackage file. And then I'm going to, similar to pandas, so GeoPandas is built upon pandas, so pretty much everything we learned with pandas works also here. So I'm going to use a head to look at the first 5 rows of my data. So municipalities dot head. I'm sure I have some typo somewhere, but hopefully not. Yeah, so I didn't have a typo, so it worked. So we loaded the data, we read the data which was in GeoPackage format, and we used .head to type to print the top 5 rows of our data. If you want to see more of your data, of course you can adjust this number, but by default it will just give you the top 5 rows. So this is our data. It is now loaded. So reading a local GPKG file is probably the easiest task for a GIS package, so it can do it very easily, like GeoPandas. But there are other functionalities for accessing data in a different way. For example, one nice thing that GeoPandas does is that it can read shape files inside a zip archive. So as I already mentioned earlier today, a shape file is not a single file, so it comes as a package. It has a bunch of files. So very often when they share shapefiles with you, it comes as a zip file, so you can just have everything in one place. And normally you have to unzip the file and then access the files. But with GeoPandas, you can just directly access the zip file, and it will just unzip it on the go and access the file. So this can be useful, for example, if you have a URL, if the data is coming from somewhere as a zip file, then you don't have to download it and then unzip it. You can just uh, access the zip file as it is. So for example, if this is an example here, if you want to get the data from this source and it's a zip file, you can just use GeoPandas read file and just give the path to the zip file. So this can be a path on your computer, a local path, or in this case it's a URL, so data is coming from the internet. So then you can just, in this example, we are seeing the head of the data. But in this case, we have the data stored locally, so it's under data directory Europe nots regions.geojson. So this is another file format we are seeing here, GeoJSON, which is web optimized. And if you just run that, you can see that you just quickly read the vector data, which was in GeoJSON format, and now you can see the first 5 rows of the data here. Okay, so let's make a new cell. So now we imported the data just from GeoJSON, but let's quickly try what it would be like. We can just copy this line. So this is how we could just test. We can get the data from this URL as a zip file. So I will just run this. And you can see it worked nicely. So we didn't download really the data before accessing it. We just got it directly as a zip file from this URL, and then we printed the head of the data. So it's identical to what we had as a GeoJSON here. So how do we write files? Simply using to_file method that comes with our data frame. So in this example, we just got the data, but we didn't really save it anywhere. So we have this nuts region. So if you want to save it, you can just easily use to_file to do that. So I'm going to use the nuts regions to_file method, and then you have to provide the path to where you want to save your data. So I'm going to again use the data directory I have defined earlier, and I'm going to save the file inside this folder as a GeoJSON file. And so you provide a name for your file. I'm going to call it Europe Nuts Regions. And then of course you provide the extension of your file. So I'm going to save it as GeoJSON, but you can save it pretty much as any formats that you saw up there supported by Fiona. So I'm saving it as a GeoJSON file. Remember to close the bracket. So let's run this. So once you do that, the data should be saved. So now if we check our data directory, we can see this new file was created 5 seconds ago. So it's just my data saved. This was just a copy of what we already had, but in real life, when you're doing analysis, you just edit your data, produce new data, and then you export it as a format that you will later need. Yeah, so if you want to learn more about what files are what kind of files can be written, you can of course check the documentation, and we already saw a bit of that up there with Fiona. But yeah, there are a lot of things you can do, so you can just check GeoPandas documentation. Another thing that we will not use in this course, but can be useful, is working with databases. Sometimes you might need to read data from databases. And the good news is that GeoPandas has a native support for read and write access to PostgreSQL or PostGIS database using GeoPandas read PostGIS function and the geodata frame to PostGIS methods for the database connection. So for the database connection, you can also use, for instance, SQL Alchemy. That is a powerful library for Python for handling just um, database operations. So you can just connect to a database and do a number of things. But the good news is that GeoPandas can natively work with these databases. Another source of data, vector data, that we use a few times during this course, and you might need it sometimes, is WFS, so World Features Service. Many organizations, including Helsinki Region InfoShare, for example, share the data through WFS URI. And the good thing is that GeoPanda can also read data directly from a WFS endpoint. And in this example, we are seeing some data coming from Helsinki Info Share, which is a place where the city of Helsinki publishes a lot of open data. Constructing a valid WFS URI is not part of this course. There are a lot of details, but just as a tip, a quick way of doing this is just starting with QGIS. So you can add the layer to QGIS and just explore it. And usually with the documentation you get, so in the info shared, there are examples how you can construct this to get your data. So there are a number of parameters you usually need to provide, but it usually looks like this. Yeah, so let's just get our data. Yeah, so now we just use WFS. We got the vector data from, so this is the population data from InfoShare Helsinki. We just fetched it through WFS from the internet, and we used GeoPanda read it as a geodata frame, and then we can just treat it as a normal geodata frame. For example, here we are using .head to get the type 5 row. So this is something that we will not cover the details of this, but we will use this quite a lot during this course for getting data from different online sources using WFS. Okay, so now we want to get it started with GeoPandas. I've been talking about it quite a lot already, starting from the first period course, GeoPython, but now it's time to get it started with that. We already saw briefly how we can read data using GeoPandas, but we haven't really started working with it so much, but now we do that. But a bit of introduction first. So as I've said multiple times already, GeoPandas is a library that is built upon pandas, as you can already guess from the name. So everything we learned in the first period, working with different panda data frames, all the things we could do with that applies here as well with the geodata frame. So in that way, we have a very good start because we are very familiar with pandas and we know how to explore and manipulate pandas data frames. And pretty much everything that we did then applies to geodata frames as well. So GeoPandas provides an easy to use interface to work with vector datasets. It combines the capabilities of pandas, the data analysis package that we got to know in the GeoPython course, for combining it with functionalities of libraries such as Shapely and Shapely, for example, for handling for geometries, or Fiona for reading and writing different data formats, and map projection libraries such as PyProj. So it brings pandas together with many geospatial related libraries and creates this powerful library for working with vector data in Python environment. So yeah, so that's what GeoPandas is. So the same definitions we saw in the first period course with GeoPandas. In lesson 5, we looked at pandas. We looked at the definitions of pandas. So what is a geodata frame, what is a data frame. So these are some of the things that we looked at in the first period. So the same things apply here. So if you remember, a geodata frame was a data frame was a two-dimensional data structure in pandas. So it looked like a table. You have columns and rows. So here, an equivalent of data frame in the world of GIS working with GeoPandas is a geodata frame. So it's similar structure as pandas. The only difference that a geodata frame has compared to a data frame is that it has a column called geometry, and that's where we hold the information about geometry, the shapely geometries that we saw in the first week. Similarly, in pandas we had series when it was one-dimensional. In GeoPandas we have geoseries that contain the geometry of the whatever we have, its points, lines, or polygons. So these are essentially the same shapely geometries that we saw in the first week. So let's get started and do a number of things. For the first cell, we have the code typed in. So we are importing the pathlib library again to define the paths a bit more systematically. We are importing GeoPandas. We are importing NumPy and Pandas to showcase a number of things. So the directory data directory is here, the data folder. And we are doing a bit of formatting things to show something on the data. And we are using now GeoPandas to read the file, and we are storing it as a variable called df, data frame. We are reading a shape file, so we know that GeoPandas can handle different file formats, and now we are reading the shape file. Let's just run this and see what we have. So this is a geodata frame. We have some columns in them and the data. We'll get back to what this data is about later on. But so this is very similar to data frames we had, with the exception that we have a column now called geodata frame called geometry, that holds the geometry information of whatever feature we have. In this case, we have polygons. So you can see the polygon coordinates represented as a well-known text. Again, this is familiar because we saw it in the first week. These are defined by shapely. These are shapely geometries. So they're represented as well-known text. And we can see, so this is what essentially makes geodata frame different from a data frame. So the input data we are working is Finnish topographic database. In this lesson, we will work with the National Land Survey data coming from the National Land Survey of Finland, or NLS for short. The structure of the data is described in the link provided. So if you want to learn more about the data, you can follow the link and do a bit of research. For this lesson, we have acquired a subset of the topographic database as shapefiles from the Helsinki region in Finland using the PyToolie. Many of you who are studying in Finland, doing GIS here, you are familiar with PyToolie, a service provided by CSC through which you can download, access different data sets provided openly by different organizations, including National Land Survey of Finland for this data set that we are using here. So this is a screenshot of PyToolie, a tool that we are familiar with, and here you can see that you can download the data. So this is where we got the data from, and now we have it already stored here in the data folder. So let's read and explore our geospatial datasets. Before we attempt to load any files, let's not forget to define a constant where we to point to our data directory. So the code is typed in. Let's just run it. So now the data directory is defined. In this lesson, we will focus on terrain objects. So it's a feature group called terrain/1 in the topographic database. So this is the information that I have gotten from the metadata. So it was with the data. I know that, so how things are called. So the terrain1 feature group contains several feature classes. Our aim in this lesson is to save all the terrain/1 feature classes into separate files. And here you can see a bit more information about different features that we have in the data. So what we want to do is to search for the files using a pattern. We have seen something similar to this in the first period working with globe. A pathlib path such as data directory path that we have already defined has a handy method to list all the files in the directory or even the subdirectories that match a certain pattern using globe. To list all shape files in our topographic database directory, we can use the following expression. So this gives us inside data directory, and then inside this folder, we look for all the files that end with shp. So they are shape files. We just want to get the shape files, and the beginning can be anything. So you can put different signs here. Again, you can check from the documentation. But if you just put a question mark, it represents any one single character. If you have an asterisk, it can represent multiple or none or one character. And if you have double asterisks, it can represent multiple characters that can include also subdirectories. So we want to search the folder and look for essentially shape files in that folder. So we can use the globe pattern search functionality to find these files. Yeah, so the first cell has the code already typed in. So let's just run that topography database directory. We are defining the directory where we have the topographic data stored. So let's just run that, and we get the path to the data. So now I want to get a list of the files that meet this meet a certain condition that I'm defining. So I will just make a list from the contents of this folder. So I'm going to just copy the name of this so I don't have to type it again. So inside this directory, I'm going to use the globe method. And here you can just define naming conditions. So I want files that start with M. They can have anything in between, but they end with P. And they are .shp, so they are shapefile. So this is what I am looking for. So I know how the file is named, not by magic, because I have checked the metadata, so I know what to look for. So how are the files named when I've gotten my data from National Land Survey? I know their naming convention, and so I know that they have defined the files like this, the files that I need for my work. So if I just run this, I will see the file that has this condition. So we can see the file is a shapefile, starts with M, ends with P, and it can be whatever in the middle, and it's a shapefile. So again, we have seen that the globe method it returns an iterator, so we can iterate through it and do your whatever you want to do. But in this case, we just wanted to do it quickly, so we just converted it to a list. So it seems that our input data has only one file that matches our search pattern. We can save its file name into a new variable, choosing the first item of the list. So I want to access that item because now I saved this as a list. But in order to access that one item where I have this path stored, I have to, of course, access the item in the list. And this is how we do it, something that we are already familiar with. So let's just run this. So I store the path to the file to input file name. So next I'm going to open the file and see what we have in the file. So for doing that, I have to import my GeoPandas library, and then I read the data into a variable called data. So using GeoPandas, I'm going to use read file function, and what I need to do is to provide the path to my file, and I've already gotten the path, so it's input underscore file name. So if I just run this, it will get my data from this path, and now it's stored under this variable called data. Yeah, so let's check our data a bit. Let's explore it like we have done before using different data types. So if I get the data type, I can see there is a GeoPandas geodata frame. So we have a two-dimensional data containing geometry. So it's a geodata frame. Then let's also look at the data head. So I'm using data.head. And you can see that, yeah, you have a number of columns in your data containing different information. And what is interesting here is that we have this geometry column and we have polygons there. So that's what makes our data a geodata frame. In pandas, we already learned how we can access column names. So as I said, almost everything we learned from pandas applies here as well. So to access the columns, I can just use data.columns, and it gives me a list of the column names in our data, which we already saw when we access the head of our data. So the data has many columns, and many of them are in Finnish. So later on we are going to rename that, but we don't need all the columns in our work. So let's select a few useful ones and also translate their name to English so it's comfortable for all of us. For example, we have a data called ryhmä, which means group in Finnish, but we are going to translate this to group to just keep it simple for all of us. Yeah, so let's just let's make a selection from our data, and this time we only keep some of the columns in our data, and we know how to do that. So you provide a list of column names that you want to keep. So in our case, I'm going to keep the ryhmä column, which means group. I'm going to also keep the class, which is called luokka. So, and of course, I want to keep my geometry, so don't forget about that. You don't want to ruin the data. So it is called geometry. Yeah, so now if we run this, we have made a subset of our data. So if we just check the data.head again, you can see that it is smaller a bit. So we have less columns. We have kept the columns that we need for our work. Then we want to rename our columns. The code is already typed in, so I'm going to rename ryhmä to group and luokka to class. We define a dictionary, and and we do the renaming using this dictionary we have defined using the old names and new names. So to make sure that everything is done correctly, I'm just going to use the data head again, and we can see that data is the same, and we have renamed the column names successfully. So many of the things that we have learned with pandas before, and this you can try on your own, apply here. So if you want to check, we learned already how we can check the number of rows in our data. You can do that. If you want to get the unique values, the same way as we did it in pandas, you can do it in GeoPandas, or you can try to see how many unique groups you have in your data. So you can try those things. But now we want to explore the data set in a map. Of course, many of us are geographers, or at least we are working with GIS, and without a map, something is missing. So let's create a very simple map. just to visualize things, just to add a bit of context to what we are doing. And doing that is very easy. Later on, we will learn how to create proper maps with all the details that we need. But for the time being, we just use .plot and we create a map. So this is similar to what we did in the first period. So pandas, and in our case now, GeoPandas is using matplotlib under the hood. So it already brings you some simple mapping or plotting functionalities. So if you just use data.plot, and in this case data is a geodata frame, so we have geometry, you can quickly make a map of your data to get an idea of what you have. So for those of us who live in Helsinki, you might already recognize the shapes here. So the data is from Helsinki area. So geometries in GeoPandas. GeoPandas takes advantage of shapely geometry objects. We already saw that last week. Geometries are stored in a column called geometry. Let's print out the first 5 rows of the column geometry. So I access the column geometry from my data geodata frame, and I'm getting the head from that. So this is what we have in the geometry column. Something we saw last week. So we have the shapely geometries, in this case polygons, that are represented as well-known text. Yeah. So since the geometries are stored as shapely objects in GeoPandas, everything we learned last week, different shapely methods that we learned for handling geometries or calculating things from our geometry, applies here as well. So let's take a quick look at this and see how it works. So I'm going to use data@, method from pandas to look at my just one of the rows in my data. So I will go with the first row of my data, and I'm accessing the geometry contents. So if you just run this, you will see the polygon. So this is similar to what we did last week. I'm just accessing that one geometry from that one row in my data. And if you want to calculate the area of this geometry, you access the geometry, then this becomes a shapely object essentially, and then from that shapely object you can just use .area, and now I'm printing this as a f string. So if I just run this, it gives me the area of that particular geometry or polygon. And here I know the coordinate system, so I dare to use the units. So it's a square meter, because I know data comes with a metric coordinate system, but we are going to look at the coordinate systems later on today. So let's do the same thing for multiple rows and explore different options of how to do this. First, use the reliable and tried iter rows pattern we learned in lesson 6 of our GeoPython course. So for index row, we can go through the first 5 rows in this example using iter rows, and we are accessing the geometry, getting the area, and then printing the area of that. So just using simple iter rows that we learned in the last period, we can do this. So let's just run this, and it's going to give me 5 lines. It has gone through the first 5 rows of data in my geodata frame, and it has printed this f string, so calculating the area from the geometry for each of the rows. So as we can see, all pandas functions such as iter rows method are available in GeoPandas. So everything you learned in the first period are going to be useful here. For those of you who have not taken the first course, I advise you to do that unless you're already familiar with pandas, because the assumption here is that we already know how pandas works, and we are just going to extend our skills using GeoPandas. So if you have forgotten how it works, I advise you to review that before continuing with GeoPandas. Of course, iter rows pattern is not the most convenient and efficient way to calculate area of many rows. Both geoseries, which are essentially geometry columns, and geodata frames have an area property. So if you want to get all the areas at once, you can just use data.area, and it's going to give you the area of all the rows, for all the polygons in your data set. So you can do the same thing for geoseries. So to get a geoseries, I'm just going to select the column geometry. So what we get as output here is basically a geoseries. So you can do the same thing with that. So I just put that area. So it can be a geodata frame or a geoseries, and you can get the area like that. And if you want to store that information in a new column, again, it's very simple. So I can just create a new column and name it area. And inside that, I'm going to store the information I got from data.area. And to just make sure I got everything right, I'm going to print the data. So yeah, so now we can see this worked very quickly. We had thousands of rows, but it just took a fraction of a second to run this. So it's very efficient. We calculated the area for each of the columns, for each of the rows in our data, and it has been added to a new column called area. So we have the area in the square meters here. So again, many of the things we learned in the first period work here. So if you want to get descriptive statistics of this, you can refer to lesson 5 of GeoPython, and we have a link here, so you can remind yourself how that works. You can, but yeah, so everything you learn from pandas works here as well. So now that we loaded the data, let's see how we can write a subset of data to the file. We learned already in the previous section how we can write an entire geodata frame to a file. We can also write a filtered subset. It doesn't make a difference. It can be the whole data set, a whole geodata frame, or a subset of that. So now we want to just, for an example, as an example, we are going to save the lakes. So we isolate the lakes in the input data, and again from National Land Survey, checking the metadata, I know that the class number for lakes in the data set is 36200. So this is the class number for lakes. So I just make a selection from my data, name it as lakes, and I'm going to later on save this as export this as a file. So let's just see what we get as output. So lakes, so if I just use type lakes, you can see that, okay, now we made a subset from our original geodata frame, and the subset is of course again a geodata frame, but this time only containing the lakes. And if you want to take a quick look at our data, of course we can use .plot to create a quick map. So these are the lakes in our study area as we selected up here. So now that we have things selected, you can export the data easily using to-file function. So lakes, the method of geodata frame, so lakes to file, then the path data directory slash the other folder you want to use inside your data directory, and the name of the file, and I'm saving it as a shapefile. So if you just run this, and if you go check out the folder, so it's in South Finland topographic database, you can see that a shapefile was created just now, where we have, so 10 seconds ago, a lakes shapefile was created. So as I told you already, shapefile is not a single file. So in this case, the shapefile, the project file, DBF, CPG, and the SHX, all the things you need in a shapefile are created at the same time. So a particularly useful method of pandas we already saw, and of course GeoPandas data frame, is the grouping function that we worked with toward the end of our GeoPython course. So group by function is a useful thing for grouping out data. It can split the data into groups based on some criteria. Then you can apply a function individually to each of these groups and combine results of such an operation into a common data structure. We have used this in lesson 6 of our GeoPython, so if you have forgotten how it works, there's a link here. You can refer to the materials and again, remind yourself of how GroupBy works in pandas, and it works in the same way in GeoPandas. But before we do that, so we want to do a grouping based on the class which includes the terrain cover. So we are going to do that, but before that, let's take another look at our data to see what we have. So remember that the class column contains information about the polygon's land use type in this data. So we saw that a certain number was referring to the lakes, so it has different values for different types. Let's check the unique values in our class. So these are the unique values we have in this column. And now we are going to use the GroupBy function to create our groups. So I'm going to name it grouped data, and then I'm going to use data.groupBy, and the column I'm using for grouping is the class column. So it's identical to what we did in the first period working with pandas. And let's just print get the output to just see how it looks like. So you can see that the output is a GroupBy object. So it's a GroupBy object, and we are going to explore this further, see how it works. To access the groups, we already see in pandas. So with grouped underscore data, I can view the groups like this. So we have a lot of, so we can get information about the groups we have. Of course, this looks messy. If you want to do this a bit more neatly, of course, we can do iteration. So we can simply iterate over the entire GroupBy object and, for example, count how many rows and data we have for each of them. So this is what we are doing in this piece of code that is already written. We have a for loop going through the group data, accessing the key and the group information, and printing the key, and also getting the length of the group. So seeing how many rows we have in each of the groups. So we can see that the numbers vary quite a lot. In some of them we have only one row, in some of them we have thousands of rows. So that there's a lot of variation there. For instance, we already looked at the lake, which had the value 36200. If you find it here, you can see that we have 56 lakes, or 50 polygons in our data labeled as lakes in the data set. So to obtain all the data, all rows that belong to one particular group, we can use the getGroup method, which returns a brand new geodata frame for us, which is handy. So let's try it for these lakes. So again, I'm recreating the geodata frame lakes, group data, get group, and this is the class value, the key value I'm using, which I know refers to lakes, and I'm checking the type. So what we get as the output is another geodata frame containing only the lakes. So similar to what we did earlier using a different method, you can create a geodata frame of your lakes using the GroupBy method. Just one thing to remember is that the index in the new data frame stays the same as in the ungrouped input data set. This can be helpful, for instance, when you want to join the group data back to the original input data. So now now that we created these groups, we want to export them as separate files. So they were all coming in one data. We created the groups. Now we want to export them as separate vector data files. So what we need to do, the code is already written there, and it's very simple. So what we do is to loop. We have a for loop, so we go through the groups, and what we do, we save each group as a file. And here in this case, I'm exporting as a shapefile. I'm saving it here, and this is how I'm naming it. So terrain, I'm using an F string to modify the name of the file. So terrain underscore, and then I'm adding the key name, so the key value in the file its name. So if I run this, it's going to create all these shape files, a shape file for each of these classes, into my topographic database directory. So note that here we combine the pathlib path that we have used already a lot today, and we combined it with an f string. So here you can have a string to name the file, and if you have f string, then you can modify the name of the file. So this is a handy thing in Python. So if you want to give unique names for your files, and in this case we have a for loop, so in each loop you have a different key, so a different name for our output file. So this is a useful way of doing things. It's a handy way of doing things. As an extra, we want to save some summary statistics to a CSV file. So one thing to note here is that whenever you export something from your geodata frame that does not include the column geometry, the output becomes automatically a pandas data frame, because a geodata frame by definition is a pandas data frame that has the geometry column. So for example, if you export the statistics as a CSV and we don't have the geometry anymore, then it's basically a data frame. So one interesting application of this is to save basic descriptive statistics of geospatial dataset into a CSV table. For instance, we might want to know the area of the training classes. So let's do this again. We start by grouping the input data by train classes, something we did before, and then we compute the sum of the area classes area. Then it can be condensed into one line of code. So instead of doing it over several cells, you just do it in one line. So I create area information, data group by class, and then I get area and calculate the sum, and then I just get the output. So you can see that we calculate the sum of the areas for each of the classes, and now it's printed out here. And of course, if you want to save it to a CSV, similar to what we did in the first period course, you can just use to_CSV, provide the path, name of the file, and the format, which I'm using CSV for, to just save the file. So if you just run this, the CSV is created, and if you go check out this folder, you will see that the CSV file is just created 14 seconds ago. Yeah, or that was it. Yeah, it's in the data folder. So yeah, that was a brief introduction to GeoPandas. Okay, before we wrap up for today, we still have one more thing we want to look at. So that's working with map projections. It's easy but very important in the world of GIS. We already had a brief overview of what CRS is. A coordinate reference system is a crucial piece of metadata for any geospatial dataset. Without CRS, the geometries would simply be a collection of coordinates in an arbitrary space, so you cannot link it to the real world. Only the CRS allows GIS software or package, in our case, like Python packages that we use in this course, to relate these coordinates to a real place on the Earth or other approximately spherical objects or planets. If you're doing the GIS on Mars, let's say, there's no reason why we can't do that. Yeah, so often it might be a bit confusing, but we all have studied GIS, so we know that we can also have projected systems. So map projections, also called as projected coordinate systems, are mathematical models that allow us to transfer coordinates on the surface of our from the surface of Earth, which is three-dimensional, into a two-dimensional world, which we, for example, use for some of the analysis. Or if you want to print out a map, which will be usually in 2D, of course, if you're printing or showing it on the screen. So working with CRS, there are a lot of details that if you have forgotten, you can check out your online sources or review some of your GIS books to remember how things work. But good news for us doing GIS with Python is that working with map projections, reading, writing, like setting the right CRS or transforming between different coordinate systems or projections is quite easy in GeoPandas. So that's the good thing. And now we will see how we can handle coordinates reference systems in GeoPandas. Uh, as I mentioned briefly earlier, there is a library that is specialized for handling projections and doing all transformations and everything related to pretty much everything related to CRS. And GeoPandas is using this library. The library is called PyProj. There's a link here if you want to learn more about the library and how it works. But GeoPandas natively, under the hood, uses this library, so it brings you a lot of functionalities. Just one caution, as I said a few times already, a shapefile is not one file, so it comes with a number of files. And one of the files that comes with a file with the shapefile is a file with the extension .prj. This file contains information about the coordinate reference system. So if you get your data from somewhere in shapefile format and the PRJ file is missing, then you don't have information about the coordinate system of your data. So you have to either define it if you know it already or do something about it. So let's start by displaying the CRS of a dataset. We will start by loading a dataset of the EU countries that has been downloaded from an online source, a unit within Eurostat that manages geospatial data for European Commission. So I start by importing the path, defining a path, importing the pathlib library and setting my data directory as usual. Then I'm going to import GeoPandas library and read my file, which is stored in my data directory under EU countries 2022 GeoPackage. Now I want to check the CRS of my data, my geodata frame. So doing that is fairly easy. Now that we have loaded our data as a geodata frame, we can just quickly check the CRS by using the name of the variable where we have stored the geodata frame and .crs. So this quickly prints out some information about the coordinate system. So we know that it's we see the EPSG for code 4326, it's WGS84, and a number of additional information about the datum and how the CRS works. So let's also take a look at our data again. So I'm just pasting the name of the variable and .geometry .head. So I'm looking at the coordinates. So very often, if there is I have a typo here, which is correct now. Very often, if you are working with a coordinate system that we are familiar with, so for example, for Finland, we know what are, if you are working, for example, with WGS84, like 4326 coordinate system, we know the ranges of coordinates for Finland, for example. So it's useful to just take a quick look at the data to see if it matches, like it corresponds. So now our data is from Finland and the coordinate system looks within the range. So one thing very often we need to do is reproject a geodata frame. A geographic coordinate system may not be, depending on what we want to do, the coordinate system that we have our data in may not be suitable for what we want to do. It can be for a number of reasons. So now in this case, this coordinate system is not a suitable one for us. It can cause distortions. So we want to use a different coordinate system, for example, Lambert azimuthal equal area projections such as 3035, and transforming between coordinate systems is very easy. So in order to do that, I'm just going to create a new variable where I will store the new data, which is the same data just in a different coordinate system. And I'm going to name it EU countries underscore EPSG, and then put the name of the EPSG. It was 335. And what I'm doing, I'm just transforming my EU countries using two CRS function. So as simple as that, I can transform to another coordinate system. And what coordinate system do we want to transform to? You can just provide the EPSG for it. So I'm going to transform to EPSG 3035. So if we run this, and I will also get the data head, you can see that the coordinates change. So we had the degrees, now we are x and y, so we don't have the longitude and latitude anymore. And yeah, so we did the transformation fairly quickly. So yeah, so as very simply using 2CR, so with .crs you can get information about the coordinate reference system that you have already assigned in your data, used in your data. And using 2CRS you can just transform to any other coordinate system you want. Here let's try a number of coordinate systems. Let's just see how things look. So now we just make a subplot. We have our data from European countries in different coordinate systems. This is the first one, the WGS84 we had originally, and this is the one that we transformed to. So you can see it changes the looks of the shapes of the polygon, so it causes distortion. So yeah, so that's a reminder that it's important to use the right coordinate system for our purpose. Yeah, so if you want to export the data, now that we exported, we can export it as a geo package, the transformed data. So I'm going to just run this and save it as a geo package under EU countries in my data directory. So there are different ways to store and represent CRS information. The more commonly used formats include the proj strings or EPSG codes or well-known text format or JSON. You will likely encounter some or all of these when working with special data combined from different sources, obtained from different sources. Being able to convert CRS information from one format to another format is needed every now and then. Not always, but sometimes you might need it. So it's useful to know a few tricks how to do that. We have already briefly mentioned that GeoPandas uses PyProj library to handle reference systems. We can use this same module to parse and convert CRS information to different formats. So this is not about the CRS itself, but the information about CRS. So the code is already typed in here. Let's just run it. So CRS, PyProj. So you can get the coordinate system information in different formats. So you can have a proj string, you can have it in well-known text like this. You can get it as EPSG code. So there are a number of ways you can get the information in different formats that might be useful to you depending on what you're doing. Well, one thing to remember is that not every possible coordinate reference system has a EPSG code assigned. Well, the most popular ones have a EPSG code, but not all of them necessarily. That's why PyProj by default tries to find the best matching EPSG definition. It does not find, if it does not find any, then 2PSG returns none. Yeah, so if you try this and there is no EPSG of matching one, then you get none as the output. You can use the PyProj to find detailed information about CRS. Of course, you can just Google, learn more, but if for whatever reason you don't have access to internet or any books and you want to learn more about a coordinate system, you can just use pyproj.crs and it gives you a bunch of information about how it is defined. You can also access individual elements from the information, so you can get the info, the name, WGS84, or if you can access from CRS the area of the used boundaries, used bounds, and then you can get the coordinates of the bounds that it is used within. Uh, now it's time to play around with some map projections. For this, you will find a global data set of country polygons in data directory. It is already saved there. It was downloaded from naturalearthdata.com, which is a great source for cartographer grade geodata. So if you haven't used it before, you can check their website and see what they have. Yeah, so now we just let's read the data. We learn from first period how we can create a plot and add a title to it. Here we added the CRS name as the title. We can see our map in Web Mercator. This is how it looks like. In Eckert, it will look like this, or if you want to have an orthographic projection centered in Finland, this is how you do it. And we have provided the coordinates for Finland for centering. This is how it will look like. So we can play with this a lot. For some of you who might later take the cartography course in the spring, we explore this even further because this has a lot of implications for how your maps look like. But for the time being, how we learned how to work with projections, with how to transform between them, and how to use them effectively when using GeoPandas. But we will be working with this a lot during this course, so you will gain more experience how to handle them.